Welcome back to ECE 442-542. Just maybe as a reminder to myself, there's more going on April 15th than taxes. You have your third exam on April 15th. As a reminder, you'll have some homeworks due before that, and they are coming soon. Homework number 5. For those of you that really enjoyed your spring break, I thought maybe we should figure out where we have been, not on spring break, but in this class. And in very general terms, we've been modeling and doing Z-transforms. We'll go over a little bit more depth than that in a minute, but where are we going? In general, we want to get to controller design since this is a controls class. But before we can get into controller design, we actually still need to figure out what we want to accomplish with our controller. What do we want our end target to look like? And that target is what I'm calling performance specifications. And we'll say, what are some ideal performance specifications or poles in the Z-plane that we would like our closed loop system to look like or to achieve? That's given to us by our performance specifications. And we'll first remind ourselves, I think we quickly started talking about that before exam number 2. You probably turned off as soon as I said this won't be on exam number 2. So we'll review that a little bit for the analog case in the S-plane, what these performance specifications look like. Then we'll try to translate those into discrete time performance specifications, pole locations, which are the desired transfer functions that we may want our closed loop system to look like. That's where we are headed. But before we get there, let's just remind ourselves of where we've been. If you have to report this back, in very broad brush ideas, we talked about the time domain and the frequency domain representation of systems. We have difference equations and transfer functions. We know how to solve those, both unforced and forced, or homogeneous and non-homogeneous difference equations, just like you can solve differential equations. We have this agreed on rule of thumb for the sample period. We can sample omega sub s to be 30 times the closed loop bandwidth, and now we'll have a better understanding maybe about the closed loop bandwidth once we start focusing on this desired closed loop transfer function. We've talked about Z-transform, there's the definition. We know how to map between the S-plane and the Z-plane. We will actually use that today to make this connection with design specifications in the continuous time with design or performance specs in the discrete time. That will be provided by this mapping. We talked about inverse Z-transform, and to make that unique, we needed this concept of region of convergence, and you did quite well on the regions of convergence on the exam. Actually, you did quite well on the entire exam. So maybe you did enjoy your spring break that way. Then we went into discrete equivalence, and we could talk about discrete equivalence in the time domain and in the frequency domain, or state space and transfer function, and we had many different ways of finding these discrete equivalents. We started with the zero-order hold, and that I think was strategy number 2 in our 2 different strategies or cases. That was when we had a hold device preceding our plant. That's when we wanted to use the zero-order hold equivalent. All the other equivalents to go from a continuous time to a discrete time involved either numerical integration, which we talked about 3 of those, or the pole zero mapping. And when we were talking about the pole zero mapping, we actually started thinking a little bit more about this concept of zeros at infinity and what that meant relative to implementation concerns. Meaning if we needed some fixed delay between when we can inject the control signal into our system and when we can compute it, we might want to force so many zeros at infinity. And some of our pole zero mapping, we talked about mapping all of those to this z+1 factor. MATLAB does all of those minus 1. It doesn't map one of those, and so it preserves one sample period of delay when it does the pole zero mapping. That's where we've been very quickly. I hope it was quick. Where are we going? It's highlighted on the screen. We want to figure out how we design that red box, that capital C of Z, these controllers. And I might call it a compensator, I might call it a controller, but it now fits into this overall block diagram. And the idea behind designing capital C of Z is to make that entire block behave the way we want it to behave. Meaning between the reference input R and the output Y, we maybe have a good idea as to how we want that performance to look or what we want the system to behave like. Meaning, if we're interested in that closed loop behavior, and if we lump it all into this capital T sub C of Z, a closed loop transfer function, which isn't just the product of C and G, is it? It's CG over 1 plus CG, if we were cheering, and you might be cheering now until at least Thursday, right? Current event. We have to inject some of these current event topics. Okay, I see some people that know what I'm talking about. The others are still on spring break. That's fine, but you will want to get back engaged with this class before exam number 3, which is when? Tax day, April 15th, so you should remember that. So what performance is needed in this closed loop transfer function? We want insight into how do we select, or what's this target that we're trying to accomplish or achieve, this capital T sub C of Z. And before exam number 2 happened, we started talking about these performance specifications in the continuous time case, and we based it on the ivory soap plant. The pure two-pole system. Pure meaning 100% pure, that's where the ivory soap comes from. No zeros, no finite zeros. We simply had 2 finite poles, and those are located according to this right parameterization at S equal to minus sigma plus and minus J omega sub D. That's one benefit of writing the parameterization as in the right. The one on the left or in the middle, for that parameterized transfer function, we have the natural frequency omega sub n and the damping ratio zeta, and sometimes it's nice to think in those terms. Where in the S-plane, the natural frequency omega sub n is the distance those poles are from the origin. That's the radial distance. And the zeta is related to the angle that those poles, these complex poles, make with the horizontal negative real axis. I'm sliding through this fairly quick, but I thought maybe you needed to attend a movie after spring break. So I'm sliding through this rather quickly. You'll have the notes, but I want to talk our way through where we're going and where we've been. If you translate, and now in this particular picture, I have shown the pole in the second quadrant and its complex conjugate twin, just to let you know that you're dealing with 2 complex conjugate poles. I'm not going to label anything for that one in the third quadrant, but it's there. But relative to the one in the second quadrant, we can identify the radial distance it makes with the origin. That's the natural frequency, omega sub n. The angle that that pole makes with the horizontal axis, we can call theta, and that's not the same theta as our theta sub d that we've talked about in the z-plane. Don't get those thetas mixed up. They're different. That's why I've tried to make that theta sub d have that subscript d to denote the difference or distinguish between those thetas. Here is the S-plane theta, and again that pole is located at a distance minus sigma plus and minus j omega sub d. And omega sub d is related to omega sub n. Maybe I did it somewhat implicitly, but omega sub d is equal to the natural frequency times the square root of 1 minus zeta squared on the right-hand side. If zeta, the damping ratio, if we don't have any damping, zeta becomes 0, and that pole, or those poles now, rotate up, and they're right on the imaginary axis. There's no damping. They just sit there and shake. And how fast do they shake? Omega sub n, the natural frequency. If we keep increasing that damping, which makes the overshoot less, then that angle theta gets smaller, and when it becomes 0, then zeta is equal to 1, and we have two real poles. Two real and equal poles. And if you look at this parameterized form for S on the right-hand side, where omega sub d, the imaginary part of those complex poles, if you plug in zeta equal to 1, the imaginary part goes away. You just have two real equal poles at minus sigma. We are concerned with that theta for, let's say, a fixed omega sub n. And omega sub n sort of determines our speed of response. Actually, the peak time is, well, I'm getting ahead of myself. There's our terminology. Sigma is zeta omega sub n. Sigma is the damping, zeta is damping ratio, omega sub n is the natural frequency, omega sub d is the damped frequency. Here is the step response of that second order underdamped system. And I've tried to label certain points on that diagram. The horizontal axis is time, and on that time axis we have the first time that it reaches a peak, which we're calling the peak time, T sub p. When that oscillating step response finally gets into a 1% tube. In this class we're worrying about the 1% settling time. When it gets within that 1% tube and never leaves, that's what we label the settling time, and that's how many time constants roughly? That's 5 time constants. What else? We have a final value, y sub fv. That's where we will eventually settle to, which we never settle theoretically, but it's approaching that final value, y sub fv. And y sub tp, we can use that with y sub fv to determine our percent overshoot. The key things on this diagram are how big that peak is at the peak time. When we get to the peak time, that tells us how quick our system is. If our peak time is really short, then it doesn't take us very long to reach the first peak, and our system is fast. If we want a fast system response, we want T sub p to be small. If we don't want much ringing in our system, we probably want that overshoot to be small, or we might want this relationship between y max and y final value to be small, which governs our percent overshoot. And we may want a somewhat quick settling time, which also is related to our speed of response. How quick do we settle? T settle. We want to now relate those time domain characteristics or specifications to pole locations in the S-plane. Where are those X's in the S-plane? Settling time, you told me, was 5 time constants. Tau is 1 over sigma. Settling time is now 5 over sigma, and if you give me a settling time, I can give you a sigma. You say you want a settling time of 500 milliseconds, or half of a second. T settle is now 1/2, and that tells you sigma needs to be where? Where are your poles in the complex S-plane? If you have a settling time of half of a second. It's not a hard answer. You're probably afraid to volunteer because you 10, thank you. But that tells you now sigma in the S-plane, you need your poles to be, if you want a settling time of 1/2 of a second, your 1% settling time to be 1/2 of a second, you need your poles, the dominant poles, the slowest poles in your system, to be beyond -10 in the left half plane. You now know that, and if you want to decrease the settling time, you need to make that sigma further off to the left in the S-plane. Settling time then translates into sigma, the horizontal distance into the left half plane. So you can make that connection. You say settling time, now you can see this vertical line in the S-plane sliding off to the left. That's one of the performance specs. Another performance spec is the percent overshoot. And if somebody gave you the response, you could compute the percent overshoot via this formula. It's just the maximum y minus the final value divided by the final value times 100%. They may actually tell you, if this is a performance specification, they may say, I want a percent overshoot of 10% or less. Then they give you PO, and if they give you PO, then you can solve for zeta, and remember what zeta is related to in the pole diagram? That's related to the angle, theta, isn't it? If we go back to this picture, if we wanted to reduce our percent overshoot, now, oh man, I'm hungry. If you view that as a wedge, that angle defining your wedge, then less overshoot says your pie or pizza wedge is smaller, isn't it? Because you want that angle theta to be smaller. If you want smaller overshoot, you now want those poles to be closer to the real axis instead of close to the imaginary axis. If somebody gives you percent overshoot, then either you have this figure that you should make sure is more accurately sketched than what I've indicated, or you can use this formula. And if you use the formula, make sure you don't forget the square root. That's a common mistake. But that's the relationship between a given percent overshoot. Now if somebody gives you 5% for an overshoot, you use the 5 for PO. PO is 5 divided by 100 in that argument for the natural log squared. And a 5% overshoot is roughly 0.7 for zeta. And now the relationship maybe, it's getting a little bit busy, isn't it? Here's the S-plane picture that you want to burn into memory if you're thinking continuous time performance specifications. If you want to decrease the percent overshoot, you're wanting your zeta value to go closer to 1, or that angle, theta 1, is going to collapse or shrink or get smaller and maybe approach theta sub 2. That will produce less overshoot. Percent overshoot translates into zeta, which is related to the angle theta, via cosine theta is equal to zeta. Finally, we're still in continuous time. Our peak time performance specification, T sub p, which I think we derived last time, is pi over omega sub d. And remember omega sub d? That's the imaginary component of these complex poles. If you want to speed up your system in terms of how quick it gets to the peak, then you want more imaginary component on those poles. You want omega sub d to increase. So decreasing time to peak, for the same sigma value, you want to have your omega sub d get larger. Time to peak then translates into omega sub d. And if somebody gives you a time to peak, they now have specified your omega sub d. If they say you want to reach your peak time at 100 milliseconds or less, now you have pi divided by 0.1 for omega sub d, or you're now at 31.4. Did everyone enjoy Pi Day over spring break? Pardon? You didn't get pi. I didn't either. I can't even, yeah. Oh, I was at a meeting and some people made a big deal about Pi Day. Oh, never mind. Thought that was big for middle schoolers, but I guess we were celebrating it too. He goes, well, I'm going to put my geek hat on and we're going to celebrate Pi Day. It's quite a way to get roused up on a Saturday. Pi was on Saturday, wasn't it? 14th of March. I'm remembering right. All right. Now, let's translate these. Now you can get out your writing utensil and start writing down with me, following along. And we want to now translate these z-plane pole locations, or translate these design specs into z-plane pole locations. And we'll do that with our trusty relationship, z is equal to e to the st. And we want to actually parameterize s consistent with zeta and omega sub n, meaning we can now rewrite z as e to the minus zeta omega sub n, that's the real part in the s-plane, plus j omega sub n square root of 1 minus zeta squared, all of that times t. And remembering that this is sigma and this piece is omega sub d. Which now we can break that into two parts by distributing that sampling period, capital T, through those two parts of that complex exponential. We now have e to the minus zeta omega sub n t, and we have another piece, e to the, how do I want to write this, j omega sub n t square root of 1 minus zeta squared. And this, remember, if you wanted to, that's sigma, and this omega sub n together with this radical is omega sub d. So that's e to the j omega sub dt, and the other part is e to the minus sigma t. We can now say that this is really just a real number, that's r, and consequently this is now r, e to the j omega sub dt, but we've actually referred to omega sub d capital T as our theta sub d. Meaning, if somebody now has specified a peak time by omega sub d, a percent overshoot by zeta, and a settling time by, what was settling time? Sigma. We have sigma sort of hiding in there in r. Now we know where we're at in the z-plane. We have r specified, we have theta sub d specified, And z now, relative to this parameterized description, in the z-plane, we now have two poles. I just have shown the positive theta sub d, but we now have the poles located a distance r from the origin. This pole right here is r e to the j theta sub d. And what we want to know now is if somebody now gives us a settling time spec, a percent overshoot spec, and a peak time spec, can we translate those into particular regions in the z-plane, just like we translated those into particular behaviors in the s-plane? Percent overshoot was pizza, wasn't it? That was the pi wedge. Settling time was the vertical line into the left half plane, and peak time was our omega sub d in the s-plane. Let's see what those look like in the z-plane, and maybe we'll look at some of those and come back and chase. So this may not be, we'll just kind of work our way through this. Let's look at the settling time specification first. And we can go from what we know, which is the s-plane, into the z-plane. And we're going to make that connection via z is equal to e to the st. Let's say that we now have poles maybe all stacked up along or with the same real part. Now we could have poles living on this. Well, that's not a very nice vertical line, but it looked okay on my tablet until I came and looked at it in the class. It's okay. So now where are those, if you had a bunch of poles on that vertical line, where would those map into in the z-plane? Those are now going to map into a circle, aren't they? Where does the imaginary axis map in the s-plane? The unit circle. So now if you think of the imaginary axis in the s-plane mapping into the unit circle, now we have sigma sub 1, which is e to the minus sigma t. That's inside the unit circle. And if I keep my colors, oh boy. You know, I said I was grading all spring break. That's not quite true, but I did appreciate one of the comments that was on one of your exams. It said, don't take off too many points for my poorly sketched circles. You've done worse in class. So if you see that 0 score on the exam distribution, you know that that hurt too much, that comment. But it sort of livened my weekend, I guess, to read that. So I appreciate the connection with my circles and yours. And I will agree, your circles looked better than especially that one. Ooh, I must still be hungry. That kind of looks like an egg or something, but it's supposed to be a circle. Okay? And we could label this and say this is now e to the minus sigma 1t. Now, what if we went further over and said, let's move our poles further into the left half plane in the S-plane, where does that map in the Z-plane? Inside or outside that blob that I've sketched? It's now smaller, isn't it? It's still a circle, and now I hope it's clear that if you want, we've sort of sketched, if you did this more and more times, you would have this bullseye pattern or concentric circles. And the closer you get into, or the smaller your circles are, the slower or faster your system responds. If you want to speed up your system, shorten your settling time, make your system settle more quickly, which of these circles would you be targeting? Your green circle or your blue circle? The blue. You want to be closer to the origin in the Z-plane. That radial distance impacts speed. And now we could say that we have one of these is, let's say, R1 is e to the minus sigma 1t. The other one, R sub 2, e to the minus sigma sub 2t. And now, whenever you hear settling time, if you're thinking about where your closed loop poles are, that now impacts your radius in the Z-plane. Settling time now, radius. Just think concentric circles. Is that clear? That's one of your design specs or performance specifications. Let's look at let's look at an example. How do we find what that R needs to be? For example, suppose we are given a particular settling time value, and we need to find what radius are we talking? What is our R value? And during this discussion, I might use the following. If somebody gives me the absolute number, numerical value for settling time, maybe half of a second, I might want to translate that relative to my sampling period, or how many sample periods does that represent. So I might represent that as capital N sub S times T. This is the, let's say, the sampling period. And N sub S is the number of sample periods to reach a given, and we're agreeing on a 1% settling time, which means that the concept that we're looking at is x at sample period N sub S is going to be R raised to the N sub S times x of 0, and we know that we want for a 1% settling time that to be consistent with 0.01 of where we started. So this is the relationship that you can recall or think about if you're trying to find the radius R for a given number of samples to be within 1% of where you started. We can cancel the initial condition, and we can now say, okay, this gives us R raised to the N sub S is 0.1, and we know now how to solve for that. Or if we let T settle, reminding ourselves to be N sub ST, so if somebody gives you the settling time in absolute terms, you can figure out what your capital N sub s is. You now are given capital N sub s. If you now take the, whoops, since I've got 0.01 on the left, let me go ahead and take base 10 log of that, so that I now have N sub s log base 10 of R equaling -2, so that now I have log base 10 of R is equal to -2 over N sub s, and I may return to that at some point in the future, so I'll label that as my star equation. And I can now solve this for the distance away from the origin in the z-plane. I can just take the anti-log, which is raise 10 to the both sides, and I now have R is equal 10 to the -2 over N sub s, and if somebody now gives you your N sub s, you can figure out the radius that you need to be in the z-plane to achieve that settling time for your dominant poles. As a number, suppose that somebody says, I want my system to be decayed in 60 samples. That now says that capital R, or the radius you want your closed loop poles to possess, is now 10 to the -2 over 60. Or now you want your poles to have a radial distance of 0.926. They're not very far inside the unit circle, are they? If you're allowing 60 sample periods before you settle or get 1% of where you started, you'll now have the magnitude of those complex poles will be 0.926. What if somebody wanted to do just the opposite and they said, well, I know my poles, the dominant poles, have a radius of R. What's going to be my settling time? We can now say, given the magnitude of our dominant poles, and how do you determine your dominant poles in the z-plane? Let's say you have 10 poles in your system and you want to find the dominant poles of those 10. Now I'm assuming they're all inside the unit circle, otherwise we wouldn't be able to talk about settling time, would we? We would have an unbounded response if we had one pole outside the unit circle. I now have all of my poles inside the unit circle. Which poles dominate my behavior? The ones that are closest to the unit circle, and usually we want the ones closer to z equal 1 because the others could be banging around a little bit, but it's really the radial distance that impacts the settling time. Now, if we go back to this star equation, we can use that to solve for capital N sub s, meaning if we just look at star, we can solve that for N sub s. And remember that N sub s needs to be an integer. N sub s is not a fraction, that's our number of samples. And we could then, who knows if I have the right notation, but we could say something like N sub s is now -2 over log base 10 of the magnitude of the poles, and I'm saying that this is now some ceiling operation, which is going to take the smallest integer exceeding the argument, if that makes sense. I hope it does. So if our answer ended up, well, let's just go through an example and maybe it will be clear. Suppose somebody finds their dominant poles and they see, oh, the radius or the magnitude of those complex poles in the z-plane are 0.8. And those are the biggest magnitude poles that you have in your system. So we'll just agree that that's going to dominate. If they're all lumped together, they're going to kind of sing together and help with the damping. But we'll just pick the biggest one and say that's what we agree to. How many samples will it take before we settle? Now we can plug that in to that formula. Ooh, boy, we have minus 2 over base 10 log of 0.8. And I guess you guys probably have your log tables memorized. And you know what the base 10 log of 0.8 is. If you don't, then you can play along. That's now minus 0.0967, or roughly minus 0.1. So we're talking a little bit bigger than 20 for this. If we looked at this, it's 20.64. So we take the smallest integer exceeding that, and this is then telling us that it will take us 21 samples to get to within 1% of where we started. And the other one was what? 60 samples? And what was its radius? You remember? I'm just trying to get you thinking, gain a little intuition into radial distance. 0.8 is 21 samples. 0.92 or 0.93 is 60. So that's how this radius impacts your settling time. If you got closer to 1, and all of this is independent of the sample period. Sample period is supposedly given, or you know what it is. So if it was 0.1, then you could figure out the absolute value of settling time based on these number of samples with that sample period. Questions on settling time and what it translates into in the z-plane? Settling time then implies some R value. Let's now look at percent overshoot. What did that translate into, or what was connected to percent overshoot in our parameterized poles in the S-plane? What did we think about when we had a given percent overshoot, or what did that translate into? Percent pizza pie, that's our wedge, isn't it? That was the zeta value. So now if we put that into, if we're given a specific percent overshoot, then we could translate that into a given zeta using the same relationship. That we talked about earlier. But now what does that look like in this z-plane? Let's see if we can make sense of constant zeta values. Here is our S-plane, and here is our z-plane. And over here in the S-plane, let's just think about some angle theta, which is consistent with zeta, where we have cosine of theta is actually the adjacent over the hypotenuse, which is zeta. If you had a specific point right there, and this was omega sub n. And that's supposed to be zeta omega sub n for the adjacent piece. Now we have z is equal to e to the st, which is e to the minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared all times t. And this is now e to the minus zeta omega sub n t, e to the j omega sub n t square root of 1 minus zeta squared. This is now r, and let's say this is e to the j theta sub d. Now for that wedge in the S-plane, can you picture a curve in the z-plane based on this parameterized form? That theta value is a fixed zeta. If we fix zeta in the z expression, and let's fix our sampling period, capital T, what varies? The radius in the S-plane, the natural frequency. If we change the radius, omega sub n, now you could think of saying, well, for a fixed zeta, maybe I look at this value for omega sub n. Maybe that's omega sub n1. Then I have another one, which is, let's say, omega sub n2. And then I have another one, omega sub n3. What does that do here? Is it clear what I'm trying to do? I'm trying to find a pattern or some kind of curve in the z-plane. What if we went to an extreme and said, well, what if zeta was actually 0? What do you know that angle line, where does that go now? If zeta is 0, where's that angle, that dashed angled line? It now goes up. Theta becomes 90 degrees, doesn't it? And we're on the imaginary axis. And what do we know the imaginary axis maps to in the z-plane? The unit circle. So we know for zeta equals 0, for no damping, we're on the unit circle in the z-plane. So now I have to draw a circle. That's zeta equals 0. But I don't have zeta equals 0. I have zeta equal something. Zeta equals such that my angle theta is, let's say, 70 degrees. What does that look like in the z-plane? Well, if we look at this, maybe we could just pick some values. We have R1, we have omega sub n. Let's say we look at omega sub n sub 1. Then R1 is e to the minus zeta omega sub n sub 1 t. So our radius is now given, but our angle theta sub d, let's say 1, is now omega sub n1 t square root of 1 minus zeta squared. And that t square root of 1 minus zeta squared, that's just a number. That's always a number for a fixed zeta. If zeta is fixed and I start varying omega sub n, my r, my radius and angle are both changing at the same time, maybe at different rates, but now you could pick r sub 2 is e to the minus zeta omega sub n sub 2t, and theta sub d sub 2 is omega sub n sub 2t square root of 1 minus zeta squared. Let me just do this for the three specific values that I and what do we know about the relationship for R1, R2, and R3? Which one is bigger, R1, R2, or R3? And these omegas I've indicated here. So omega sub n1 is closer to the origin in the S-plane. Omega sub n2 is further away, and omega sub n3 is the furthest away. For those omegas, then is it clear what's happening to R and the different R's? We have R3 is less than R sub 2 is less than R sub 1. R sub 1 is the biggest. Is that true? As the natural frequency gets bigger, the R's start getting smaller. And for each of those R's, what happens to our thetas? T square root of 1 minus zeta squared, that's fixed for all of those. And now we're just making omega sub n bigger. So those are getting bigger also, aren't they? Well, I'm sorry. That's not consistent. The R's are getting smaller. The thetas are getting bigger. Is that clear? Meaning theta d1 is less than theta d2 is less than theta d3. Did I say that right? So now the radius is collapsing as the angle is getting bigger. Can you visualize what that looks like in the z-plane? It's a spiral. And if we were closer, if we were more than a month prior to this, I would have done this on Valentine's Day, because that spiral actually sort of looks like a heart. Humor me. So now what I'm trying to say is the radius, let's say there is R1 theta D1, then we have a smaller radius and a bigger theta D1, and then we have a smaller radius, so that this is like that. That's for a fixed zeta. A fixed what? Percent overshoot has this logarithmic spiral shape. And if we increase zeta, which way is this curve going to move? Is it going to move towards the unit circle or towards the real line? These spirals are eventually going to sort of collapse, and they'll become right on the real axis. and they're coming from the unit circle. And the unit circle is zeta equals 0. The real line is zeta equal 1. So these logarithmic spirals, as you reduce the percent overshoot, is that okay? The percent overshoot decreases. Those logarithmic spirals, the region that you are allowing your poles to live in is now shrinking. If you want your percent overshoot less, your heart is getting smaller. That's maybe bad. Because we all want big hearts, right? Well, I guess healthy hearts are not big, but the metaphor, we want to have a big heart. Sorry. Spent part of my day with a biomedical engineer, so I guess I'm thinking about hearts. And he's probably thinking, your heart's not very big, buddy. Okay, possibilities. What do we have? We could have two different specifications given to us. Somebody might say, oh, I want a given settling time and a particular percent overshoot. Those two are now specified. What does that tell you about your desired pole locations? Let's now remind ourselves what this means. If somebody gives you a settling time spec, what does that lead to in terms of a picture in the z-plane? That's the radius. That's our r value. So now we know a r value. And what if somebody now gives us a percent overshoot? That leads to a logarithmic spiral, a zeta. So now we need to find, given a percent overshoot and a settling time, where are our closed loop poles? Where are desired closed loop poles? We now are given R and zeta. We now want to find, let's say, our desired poles. That's supposed to be a delta. It's supposed to be a delta. Z sub delta is R e to the j theta sub d. If that was R e to the j zeta, we'd be good, because we know R and zeta. But the poles are some radius away and some angle away from the origin. We now have a radius and a logarithmic spiral. We need to find the intersection of those two curves. And we can find those by parameterizing this angle, theta sub d, in terms of r and zeta. So let's see if we can make that happen. We're trying to find theta sub d. Is it clear what we're looking for? How is r parameterized? That was e to the minus sigma t, but sigma is zeta omega sub n. We now know r is e to the minus zeta omega sub n t. If we take the natural log of both sides, we can now sort of isolate some of the terms. we need to keep zeta and r alive in our expression. Let's now solve for the natural frequency in the sampling period. This is now minus zeta over, whoops, is minus natural log of r over zeta, solving for omega sub nt. But we know the way that we've parameterized theta sub d. Theta sub d was omega sub dt, but omega sub d was this omega sub n, I'm going to put the t there, square root of 1 minus zeta squared. It was omega sub n square root of 1 minus zeta squared times t, but we now have omega sub nt in terms of r and zeta, because we wanted to find an expression for theta sub d in terms of r and zeta. Now we have it. Meaning we can now put theta sub d is equal to minus natural log of r over zeta times the square root of 1 minus zeta squared. So that now if somebody gives us design specifications in terms of settling time and percent overshoot, we now know what z delta is. That's r. That's from the settling time. And the percent overshoot with the settling time, the percent overshoot with the settling time allows us to solve for theta sub d in terms of r and zeta. And now we know where the poles are located. They're located at r e to the j theta sub d. What if somebody gave us a different combination? Suppose somebody gave us zeta. What's that equivalent to? What have they maybe given us? Instead of zeta directly, maybe they've given us what kind of a performance spec? Percent overshoot. And what if they give us theta sub d, or the peak time? Hopefully we'll get to that in a minute, but let's show that relationship in a minute. The theta sub d peak time relationship. We want to now, given the percent overshoot and peak time, we want to find z delta, which is r e to the j theta sub d. We're given theta sub d. Now we have to figure out the radius from zeta and theta sub d. If somebody gives us percent overshoot and peak time, they haven't given us exactly what we need to find our dominant poles. But we do still know this parameterized form for theta sub d. That's omega sub dt, which is omega sub n square root of 1 minus zeta squared times t, which is omega sub nt square root of 1 minus zeta squared. And now we can solve for this product of omega sub n capital T in terms of theta sub d and zeta, and that's what we were given. This is now theta sub d over the square root of 1 minus zeta squared. Which says that r, which is e to the minus zeta omega sub nt, is now e to the minus zeta theta sub d over the square root of 1 minus zeta squared. and R now is expressed in terms of zeta and theta sub d. Theta sub d we had, that was given, and now this R allows us to plug in what we need. So we've looked at most of these, but now let's look at this peak time in particular to try to develop this theta sub d relationship with time to peak. Time to peak is pi over omega sub d, or if somebody gives you the time to peak, you can solve for omega sub d. But what do we know about theta sub d? That's just omega sub d times capital T, which is now pi capital T over time to peak. And what does this translate into if we have an S-plane picture and a Z-plane picture? Again, we're doing this mapping. Z is equal to e to the st, where we might have this j omega sub d1, and we might have another horizontal line j omega sub d2. Which gives us a shorter time to peak, omega sub d1 or omega sub d sub 2? We need a bigger imaginary component to give us a quicker or a faster response. Now, what do those two lines translate into in the z-plane? We now know that theta sub d is omega sub dt. And theta sub d is just the angle in the z-plane, which says that this might be theta d1, and this might be theta sub d sub 2. Meaning if we want a quicker responding system, we need our poles to have a larger angle in the z-plane, consistent with a larger imaginary component in the s-plane. Let's look at an example of that. Suppose we're told that the time to peak is 6 sample periods. Theta sub d is omega sub dt, but remember what omega sub d was? That's pi over time to peak, so we can say pi over time to peak times t. But we just said time to peak was 6 sample periods. That's 6 times capital T times t, so that our angle theta sub d, to achieve a peak time of 6 samples, is pi over 6, or if you're thinking in terms of degrees, it's now 30 degrees. So if you wanted your peak time to occur in 6 samples, then you would need your theta sub d to be 30 degrees or bigger if you wanted a smaller time to peak than 6 sample periods. You can also connect this theta sub d with the number of samples in one cycle of oscillation. Let me try to communicate that. So also, theta sub d can influence the number of samples per oscillation cycle. Suppose somebody gives you a theta sub d of 60 degrees. Then that actually tells you the number of samples per oscillation cycle, which I'm denoting as n right now. That's now 360 degrees divided by theta sub d, or we now have 6 samples per cycle of oscillation. By that, I'm trying to communicate the following. If we had this picture, a decaying sinusoid, it's not decaying very effectively, but where is one cycle of that oscillation? That starts here and finishes, let's say, right there. And now what we want to do is we want to actually have, if we start at 0, we want 6, and then 7 would be that next peak. So with 6 samples per oscillation cycle, we're looking at those are supposed to be uniformly distributed between the 2 peaks. Is it clear what I'm trying to say with capital N? Capital N is the number of samples per cycle. Or you could say N sub d theta sub d is 360 degrees, or 2 pi, where this is now the z-plane angle, and this is the number of samples per cycle. Suppose someone wants N sub d samples per cycle. Then they're basically specifying theta sub d. They're saying that that's now 2 pi over N sub d in radians, or theta sub d is 360 degrees over N sub d in degrees. Example, if N sub d is 10 samples per cycle, theta sub d is now 2 pi over 10, or 360 degrees over 10, or that's now 36 degrees. Now, what I may do offline, I don't know, maybe I'll do it and discuss it next time, is I might build a table that shows, given certain design specifications, what expressions you can use for R, zeta, and theta sub d to translate those into pole locations. But do you see what, let me just, boy, I shouldn't say anything about next time before it is next time, but if I give you 3 design specifications, settling time, what's that give you in the z-plane? If this is now the z-plane, settling time translates into what picture? Radius. So now we have that. Now you have a percent overshoot. What's that translate into? Some logarithmic spiral. And peak time. Some angle. Whoops, I don't like it because that's too consistent. Now maybe you have an angle there. You may need to have those 3 specifications consistent, and they may not be. You may have to tighten one specification versus the other 2. Is it clear what you have now on your table in terms of design specs and translating those into desired poles in the z-plane?